In this video, we are going to explore converter that can convert DC input to AC output voltage. A power inverter or inverter is a power electronic device or circuitry that changes direct current to alternating current. Inverters are very useful since they allow DC sources such as solar panels or batteries to AC loads such as commercial loads, the electric grid, and to motor control, speed, and direction. There are various types of inverters such as modified sine wave, pure sine wave, square wave, multi-level, resonant inverters, and many more. But only the main three levels will be discussed. First is the modified sine wave inverters. The output of a modified square wave, quasi-square, or modified sine wave inverter is similar to a square wave output except that the output goes to 0 volts for a time before switching positive or negative. So this is the wave of a modified sine wave. Second is the pure sine wave inverters. A pure sine wave inverter is the best form of inverter as it produces perfect sine wave and the energy dissipation in it is minimal. Pure sine wave inverter is compatible with all electrical devices except for sensitive or specialized equipment such as laser printers, audio equipments, and many more. Also, the output voltage in our convenience outlet is in the form of sine wave. Its designing is complicated as compared to all other inverters. So this is the wave of a pure sine wave alternating voltage. Third is the square wave inverters. The square wave output has a high harmonic content not suitable for certain AC loads such as motors or transformers. Square wave units were the pioneers of inverter development. We will simulate this one later. The square wave inverter output waveform. Control. Inverter topologies. There are many different power circuit topologies and control strategies used in inverter designs. Different design topologies address various issues that may be more or less important depending on the way that the inverter is intended to be used. First topology of inverter is the half-bridge voltage source inverters. Figure 15.2 shows the power topology of half-bridge voltage source inverter, where two large capacitors are required to provide neutral point N, such that each capacitor maintains a voltage Vi divided by 2. This one. Because the current harmonics injected by the operation of the inverter are low-order harmonics. A set of large capacitors is required, the C plus and the C minus, or C1 and C2. It is clear that both switches S1 and S2 cannot be on simultaneously because short circuit across the DC-link voltage source would be produced. The single-phase voltage source half-bridge inverters are meant for lower voltage applications and are commonly used in power supplies. Table 15.1 switch states for a half-bridge single-phase, VSI. We have here switch positive and switch negative. First stage is the switch positive is on and switch negative is off, means this switch is closed and this one is open. So at this output voltage, we will have a closed loop here, knowing that we have voltage at C plus to be equal to input voltage divided by 2. And at the output, using KVL equation, we will have VI over 2. Next stage is when S negative is on and S positive is off. If we take a loop again at this point, since positive is on, so there will be no current flowing in this path. Ito'y lang from neutral, positive to negative, VO back to neutral. So we will have output voltage equal to negative VI over 2. S positive and S negative are all off. So we have output voltage will be equal to negative input voltage divided by 2 and positive input voltage divided by 2. So here is the simple circuit diagram of figure 15.2. This EDC over 2 is our capacitor a while ago, and this load was our this one connected in our output voltage. So we will consider a resistive load here, and also we have a switches S1 and S2. This is the simplified circuit of figure 15.2 a while ago. We have here EDC over 2, so this is our voltage at the capacitor, or maybe a battery na lang. And the other half is here, EDC over 2 also. We have two switches, S1 and S2, and our load, we'll consider a resistive load here. And our output voltage is 0.AO. From our KVL equation, if this switch is on and S2 is off, there will be a current flowing in this loop. So formulating the equation in this loop, entering to the negative is positive EDC all over 2. Positive, negative, so minus VO is equal to 0. It's VO. Oh. So our VO will be VO will be equal to EDC over 2. If we consider S2 to be on and S1 to be off, so off, and S1 is off, so there will be a closed loop here. The loop entering to the negative of a battery is positive, so we have positive E DC all over 2 Then entering into the negative of the output voltage. So plus the output here, that is your V output, equal to 0. So our output voltage will be equal to negative of DC over 2. Because it is impossible for us to switch on and off this S1 and S2 manually, we can control these switches by using the PWM or the pulse width modulation. Because in one cycle, for example, is 60 Hz, if we will try to switch on and off this S1 and S2 manually 60 times per second, so it is impossible. So that's why we need to use an intelligent switch for us to get the average value of that sine wave or of that kind of wave. Pulse width modulation or PWM. It is a method of reducing the average power delivered by an electrical signal by effectively chopping it up into discrete parts. The average value of voltage and current fed to the load is controlled by turning the switch between supply and load on and off at a fast rate. The longer the switch is on compared to the off periods, the higher the total power supplied to the load. I tried to simulate our half-bridge circuit a while ago, and I used the PWM1 and PWM2 for switch 1 and switch 2 to send signal to the switches for them to switch on and off 60 times in a second. So our value of VDC over 2 is 12 volts. Same here. And also, our resistive load is 100 ohms. The specification of this PWM1, its initial voltage is at 0. It will on at 1 volt. And the period delay is 0. The T rise is 1 nanosecond. The T falls is 1 nanosecond. And the period on is 8 milliseconds. And the total period is 16 milliseconds. This PWM2, the initial voltage is 0. It will on at 1 volt. The period delay is 8 milliseconds. The T rise is 1 nanosecond. The T falls is 1 nanosecond. The T on or the period which it is on is 8 milliseconds, and also the total period of the cycle is 16 milliseconds. So I use 60 Hz for this signal. If we run this circuit, we will have this waveform of the PWM1. So one period is 16 milliseconds, this one. And this PWM1 will on at 1 volt. It will last at 8 milliseconds and it will drop at 0 volts and it will off. Then S2 will on and S1 will be off. Next one is the S2 being turned on and S1 turned off. The blue line here S2 will be turned on at 8 milliseconds and has a voltage of 1 volt, and it will be on at another 8 milliseconds until it will drop at 16 milliseconds. Next one is the S2 being turned on and S1 turned off. The blue line here, S2 will be turned on at 8 milliseconds and has a voltage of 1 volt, and it will be on at another 8 milliseconds until it will drop at 16 milliseconds. This is our input DC voltage, so it is a unidirectional, and the total voltage is equal to 24 volts. Converted into an alternating voltage, this is measured at the load. So, from straight line DC voltage, it became alternating. So, alternating because it alternates from positive 12 volts to negative 12 volts. So, this is one cycle, 16 milliseconds. The second topology of inverter is the full bridge voltage source inverters. A full bridge single-phase inverter is a switching device that generates a square wave AC output voltage on the application of DC input by adjusting the switch, turning on and off based on the appropriate switching sequence, where the output voltage generated is of the form positive BDC, negative BDC, or 0. The construction of full bridge inverter is it consists of 4 choppers, where each chopper consists of a pair of transistor. Transistors can be the IGBT or MOSFET, or a thyristor and a diode. So these are the diode. These are either thyristor or a transistor. Pair connected together, that is T1 and D1 are connected in parallel. T3 and D2 are connected in parallel. T4 and D1 are connected in parallel, and T2 and D2 connected in parallel. And all of these connections are connected via DC input voltage. The output voltage is at the load. So this is the equivalent circuit of this complicated. We have 4 switches, 4 switches, and at the center is the load. And it is connected to a DC source. So the expected output in our load is an alternating waveform, either square wave, sine wave, modified sine wave, or any. If S1 and S2 are on and S3 and S4 are off, so S1 and S2 will be closed. Using KVL equation, there will be a current flowing here. So this is your source voltage, Vs. This is your load, output voltage. Let's say this is positive, negative, VO. So KVL equation, at this loop, we have positive Vs minus Vo equal to 0. So your output voltage will be equal to source voltage. This is S1 and S2. But if your S1 and S2 are open and S3 and S4 are closed, so positive, negative, VO. Current flowing here. You will have a KVL equation Vs plus Vo equals to 0. So your output voltage will be Vs, negative Vs. I simulated the circuit diagram of a full bridge or H-bridge inverter. I use the PWM or the pulse width modulation. So 4 PWM for 4 switches connected in a 100 ohm resistor and a 200 volts DC source. This is the output waveform when switch 1 and switch 2 are on and 3 and 4 are off. So as you can see, simultaneously, they are on at 1 volt. This is switch 1 and this is switch 2. This is now the output of switch 3 and switch 4 that are on. 1 and 2 are off. So here, we can see that a while ago, switch 1 and switch 2 are in 1 volt position. But now, they are off. So, alternate yung pag-on and off ng switches 1, 2, 3, and 4. Switch 1 and switch 2 simultaneously on, while 3 and 4 are off. And then, switch 3 and 4 will on, and then 1 and 2 naman yung off. So, the final output voltage will be this one. We got this waveform by subtracting the voltage at points, this point and this point. Point, let's say 0 and point 1. I-subtract natin yung voltage at that node and this node, you will get this waveform by simply applying the nodal theorem in our circuits 1. So, We have here a square waveform, and it is alternating current voltage because it alternates from positive cycle to negative half cycle. These are the advantages of single-phase full-bridge inverter. I will not discuss in this video the three-phase full-bridge or half-bridge inverter, only the single-phase. So these are the following advantages: the absence of voltage fluctuation in the circuit, suitable for high input voltage, energy efficient, the current rating of the power devices is equal to the load current. While the disadvantages of a single-phase full-bridge inverter are the following: the efficiency of full-bridge inverter, which is 95%, is less than half the bridge inverter, which is 99%. So losses are high in full bridge and high noise. These are the applications of a full bridge inverter. Number 1, applicable in applications like low and medium power, example square wave or the quasi-square wave voltage. A sinusoidal wave which is distorted is used as input in high power applications. Using high-speed power semiconductor devices, the harmonic contents at the output can be reduced by PWM techniques. So other applications like AC variable motor, heating induction device, standby power supply. Also, it is applied in solar inverters and compressors. Only the basic operations were discussed in this video. This ends my presentation. Thank you for listening.